Welcome to this explainer. Okay, picture this. You're standing right in front of a massive, 22-meter-tall steel sphere. Inside that giant structure, highly volatile liquefied petroleum gas, or LPG. Now, in the high-stakes world of hydrocarbon logistics, getting your measurements exactly right is absolutely crucial for both your safety and your bottom line. And here's a mind-blowing fact to kick us off. Inside a Horton sphere of this size, a variance of just a single millimeter in your level measurement translates to literally thousands of metric tons of unaccounted-for product. We are talking about massive commercial vulnerabilities and very real plant risks if your numbers are off by even a fraction of a hair. Okay, let's dive straight into this. How do you actually measure a boiling liquid that you can't even see? It's a gripping question, right? You've got the sealed pressure vessel operating under totally extreme conditions. We're talking up to 18 bar of pressure during peak summer heat. Because the product is flammable and under all that pressure, you obviously can't just pop the hatch for a manual dip check. The liquid is completely sealed off from the outside world. So you need an automated measurement system that acts as a fortress-like pressure boundary while simultaneously giving you flawless, pinpoint precision. To wrap our heads around why this is so incredibly tough, we have to look at the intense thermodynamic battle happening inside that tank. The liquid phase of LPG has a really high coefficient of thermal expansion. Basically, that means its density drops off a cliff as temperatures rise. If ambient pressure drops, you get immediate flashing right at the surface, causing boiling, bubbling, and just intense turbulence. Sitting right above that liquid is the vapor phase, but this isn't just normal, empty air. It's packed with dense hydrocarbon molecules. The dielectric constant of this vapor mix actually shifts around with the pressure and temperature. Trying to shoot standard radar waves through this vapor space is literally like trying to see through a foggy, continuously shifting mirror. The waves actually slow down, which gives you totally false readings. So, in this explainer, we're going to demystify this massive engineering puzzle, step by step. First, the LPG storage challenge. Second, Archimedes and force balance. Third, the anatomy of a servo gauge. Fourth, density and interface tracking. And finally, total tank management. Let's start with part one, the LPG storage challenge, and exactly why traditional vessels and measurement tools totally fail under these extreme conditions. The Horton sphere is, well, geometrically brilliant for distributing internal pressure evenly across its steel skin, but there is a catch. Think about the cubic relationship equation here. The volumetric sensitivity of a sphere changes constantly depending on the height. Right near the equator of the sphere, a single millimeter shift represents a completely massive volume of product. But what's even wilder is this phenomenon called shell breathing. A temperature spike of just 20 degrees Celsius can actually expand the steel shell's radius by several millimeters. So the tank itself is literally growing and shrinking throughout the day, constantly shifting your true internal volume. Now, what's really interesting about this breakdown is how different measurement technologies hold up or fail against these challenges. Differential pressure relies on stable density, which, as we know, LPG definitely does not have. Guided wave radar and non-contact FMCW radar, they both suffer big time from those vapor phase propagation delays we just talked about. But look over at the far right. The intelligent servo gauge completely dominates the competition. It boasts custody transfer accuracy of plus or minus 0.7 millimeters, and it's totally unaffected by changing vapor compositions. It just completely bypasses the propagation delays that totally plague radar systems. So how does it pull that off? That brings us to section 2, Archimedes and force balance. We're applying some classic physics to modern metrology. The intelligent servo gauge relies heavily on Archimedes' principle. Just think about stepping into a bathtub. The water level rises, and your body actually feels lighter, right? That's because you're being buoyed up by a force equal to the weight of the water you just displaced. It is absolutely incredible to think that we're using this ancient, fundamental math concept to solve a highly technical, modern 20-bar industrial problem.
Here is the microstory of the gauge in action. You've got a small, uniquely shaped weight called a displacer, suspended by a thin wire. As this displacer lowers down into the tank and touches the liquid, it immediately experiences that upward buoyant force. This actually reduces the net tension on the wire. A high-speed microprocessor reads that exact wire tension and feeds it into a dedicated PID, or proportional integral derivative, control loop. The computer doesn't want the displacer to just float around arbitrarily. It actively commands a stepper motor to adjust the wire height until that displacer is submerged exactly 50%. If the liquid level rises, the buoyancy goes up, the wire tension drops, and the motor instantly winds the wire up to maintain that perfect 50% balance.
By continuously tracking that delicate force balance, the instrument achieves an absolutely incredible standard operational resolution of 0.1 millimeters. The shaft of the wire drum is directly linked to an absolute optical rotary encoder. Because the gauge's onboard memory knows the exact, precise circumference of the drum, it translates every tiny fractional rotation into microscopic vertical precision. Moving right along to Section 3, Anatomy of a Servo Gauge. Let's look at the actual component engineering that makes surviving this environment possible. Honestly, the materials used here are basically metallurgical superpowers. The displacer itself is a solid core machined from stainless steel 316L or Hastelloy, which guarantees it won't just collapse under 20 bar pressure. The wire is this precision-drawn 0.15 millimeter Hastelloy strand that winds onto a helically grooved drum. That grooving ensures every single wrap sits perfectly without ever overlapping and messing up the diameter. So, the crucial point here is the displacer's aerodynamic conical shape. Because it's perfectly smooth, it literally sheds paraffin waxes and light end residues as it moves through the liquid. This prevents any gunky product buildup that would otherwise alter its perfectly calibrated mass. Now, this is a brilliant safety feature. How do you pass the physical rotational movement of the wire drum inside to the electronics outside without creating a hole for explosive LPG to leak out of? Well, you use a solid non-magnetic alloy barrier. Torque and force are transmitted straight through this solid metal wall using high coercivity rare earth samarium cobalt magnets. The inner magnetic ring perfectly aligns with the outer magnetic ring. There are no physical mechanical shafts and no dynamic lip seals to wear out or leak. It is absolute 100% isolation. Inside the tank, the mechanical installation is just as critical. The gauge is never just mounted over open liquid. It sits securely atop a 4 to 6 inch vertical pipe called a stilling well. This acts as a protective shield against surface boiling and thermal convection currents. Precision slots let the liquid equalize inside without all the violent waves. And the tolerance here is laser straight. Maximum vertical deviation cannot exceed plus or minus 0.1 degrees, ensuring the displacer wire never, ever rubs against the walls. Plus, a solid datum plate at the absolute bottom provides a permanent fixed point for 0-point calibration. All right, now for the gauge's advanced superpowers, Section 4, Density and Interface Tracking, where we explore some of the more advanced tracking modes. So, over time, heavy water naturally separates from pressurized LPG and sinks right to the bottom of the Horton sphere. If you leave it undetected, it causes severe corrosion. Enter interface tracking mode. Here, the gauge acts like a robotic scout. It drops the displacer all the way down to the bottom. The exact moment it hits that water layer, the higher density of the water creates a sudden, sharp spike in buoyant force. The gauge locks onto that instantly, finding the exact water line so operators can safely and efficiently drain it. Beyond just finding hidden water, the gauge also performs density profiling. Because LPG composition varies, it creates layers of different temperatures and densities in the tank. Instead of forcing someone to take manual samples, the gauge lowers the displacer and stops it completely at pre-programmed depths, say every single meter. By reading the absolute wire tension force at every stop, the onboard microprocessor uses a fluid density equation to map out a real-time vertical density profile of the entire tank. It's incredibly smart. Section 5, Total Tank Management and Digital Integration. Let's connect all this raw physical data we've gathered to actual plant profitability. Since LPG expands and contracts so wildly with temperature changes, simply knowing the level and density just isn't enough. The servo gauge talks directly to a multi-spot temperature element, or MST, which sits in an adjacent thermal well. The gauge tells the system exactly where the liquid level currently is, so the system then averages the temperature readings only from the specific RTD sensors that are actually submerged. It totally ignores the vapor space, giving you a highly accurate liquid temperature adjustment. Let's see how all this data builds into our final commercial metrics. We push it through this exact pipeline, which, by the way, is strictly required for API MPMS compliance and custody transfer. Step 1, the raw level calculates the total observed volume. Step 2, we subtract the water we found earlier to get the gross observed volume. Step 3, we apply the exact temperature correction to find the gross standard volume. And finally, step 4, we multiply by the standard reference density to arrive at the total commercial mass. This right here is the exact number used for your financial accounting. When you look at the big picture, this entire explainer really comes down to one simple truth. Every millimeter matters. The incredibly elegant mechanical physics of the intelligent servo gauge, the conical displacer, the precise force balance PID loop, that ingenious rare earth magnetic coupling, they all work together flawlessly to secure plant safety and protect massive financial investments from the absolute chaos of thermodynamic fluctuations. Which leaves us with this final thought to ponder. When you're dealing with a boiling, pressurized liquid that you literally cannot even see, in an industry where a single millimeter error costs thousands of metric tons of product, can you really afford to guess? Thank you so much for joining me on this explainer. Keep learning, keep measuring, and I'll see you in the next one.